Okay, we're going to continue on here, chapter 15, solutions, and hopefully finished up. So we've been talking about solutions here. And last time we focused on a few things, including, I think, molarity, which is our moles per liter. Remember that is our moles of our solute per liter of solution is really what it is. And it is an equation that we could kind of use like a formula, and we do rearrange this and solve for pretty much any of these three things here. We could solve for liters, which would be moles divided by molarity. We could also solve for moles, which would be liters times molarity. And remember, as we talked about, you want to make sure that always when you're using molarity by itself, you do use liters for the volume. Otherwise, once again, you will probably be off of what you're looking for. You most likely be looking for moles. You'll actually end up with millimoles if you don't convert it out of milliliters. So you want to make sure that you definitely use liters with the molarity. We also talked about dilution. And remember that dilution is really when we add more solvent. In a lot of cases, our solvent is water. And when we add more solvent, pretty much what we are adding is more of the bottom part here, which is the volume of solution. And the result of that is the volume of solution will go up, but the moles of solute will remain the same. And because that volume of solution goes up, basically, we do see a decrease in the molarity when we do a dilution. And there's a couple of different sort of formulas that can be used for dilution. M1 V1 is equal to M2 V2. That is probably most of the time what people will use, because as we've talked about, the most common unit of concentration is molarity. So oftentimes we do sort of use this equation. Remember as well, if you are using this equation, it is okay to leave it in milliliters. But again, if you are not using the dilution equation, but just the molarity sort of formula, you want to make sure always it's in liters so you'll have the right units. A more generic version of this equation is C1 V1 is equal to C2 V2. And in this case, C is just generic for concentration. Although molarity is the most sort of common unit of concentration, you technically can use any unit of concentration in this formula. I can use percent mass to mass, percent volume to volume, whatever it may be as well. So sometimes people will use C1 V1 equals C2 V2, but a lot of times people will use this sort of equation here. We sort of finished up talking about sort of stoichiometry that involves. And really, the good news on that is it really is the same sort of steps as traditional stoichiometry problems, with one or two sort of differences. There may be something that you do, but it really does boil down to the same sort of process. And that basically means that you got to start with your balanced equation. You need to convert to moles, so that's pretty much normal fare. Remember as well that you do need to sort of analyze your stoichiometry problem, whether it be just a basic stoichiometry, a regular stoichiometry problem, solution stoichiometry, gas stoichiometry, whatever type of stoichiometry problem it is. You want to make sure that it is either not a limiting reagent problem or it is a limiting reagent problem. Remember to determine if it is a limiting reagent problem, pretty much you need to be given enough information to calculate the moles of basically both reactants. So if whatever is given to you in that problem, there's some way for you to get basically 2 moles of each of the reactants, then it definitely is a limiting reagent problem. And you need to do some type of calculation to determine which one is the limiting reagent. You can't just pick. If you do not have enough information given to you to get the moles of both reactants, then it really is just a basic sort of stoichiometry problem. You don't have to worry about the limiting reagent aspect of it. So optional here-ish sometimes is, again, if it is a limiting reagent problem, you got to do that additional step. And it's the same sort of step that we've done in regular limiting reagent problems. You could do a little calculation and figure out, again, if you want to use up one of your reactants, how much of the other one you need to put in there. I could also figure out how much product each one makes. So again, you could do it either way. Regardless of which way it is, either limiting reagent or regular stoichiometry problem, you will then continue on to the next step, which is really the stoichiometry part of it. And that is the mole-to-mole relationship from the balanced equation. And last here, you will always be in moles at this point. You will convert to some other units. So really where sort of solution stoichiometry, again, sort of varies from regular stoichiometry problem is usually in two spots here. One spot is usually right here. So instead of in a sort of traditional stoichiometry problem where we use grams and the molar mass from the periodic table to figure out the moles, we pretty much get the moles using this relationship here, that the moles is liters times molarity. The other sort of difference usually will come at the end. And, there's a few different maybe options as to what you could do at the end of the problem. So at the end of the problem, you can definitely go like we've done before. Maybe we did in a couple of examples last time. You could take moles and go back to grams. And once again, that is the molar mass from the periodic table that allows you to do that. Also very common. Maybe you'll take the moles that you calculated from the stoichiometry part, and maybe they will give you the molarity. So using both of those, you could really get the volume of the solution that you're looking for. Lastly, maybe you use the moles that you calculated from stoichiometry and the volume that they give you to calculate something like the molarity. So those are sort of three sort of outcomes that you could come or get from a solution stoichiometry. I would say probably in most cases, or a lot of cases, you might use all three of these, but either figuring out the volume or the molarity is a very common sort of end sort of calculation that you do there. Any questions on any of that there that we talked about last time? All right, so let's talk about one last sort of solution stoichiometry sort of situation, and that really is neutralization sort of reaction. And that is what happens when you take an acid and a base together, much like what you did hopefully on Monday through titrations, and what you'll do today as well as you continue your titrations. But whenever you take really an acid and you react it with a base, you do get two things. You do get a salt, which is an ionic compound, and you do get water. So that's an ionic compound. And really, any combination of a strong acid plus a strong base, basically the overall reaction that's really taking place is that formation of water, like we talked about when we talked about types of reactions. So if you took something like hydrochloric acid and some sodium hydroxide. So hydrochloric acid is a strong acid, sodium hydroxide is a strong base. And if you reacted those together, remember, this is really a double displacement reaction, positive, negative guy sort of happening there. And we will get our water. And again, the water in this type of situation from a strong acid and strong base will always come from those two parts right there, the H from the acid, the OH from the base. And really the salt will come from what is left over, these two guys basically coming together properly, which will give us sodium is +1, chloride that is -1 will give us something like sodium chloride in this particular case. If we were to write our total ionic equation or complete ionic equation like we talked about in the past, we would break apart the hydrochloric acid as it's a strong electrolyte and will 100% break apart. Same thing with our sodium hydroxide, which is a strong acid, strong base, which will also break apart. Our water here will stay together. Remember that when you write these type of equations, in addition to making sure that you have charges, because they are a total ionic equation, anything that is a liquid, a solid, a gas, anything that is a weak electrolyte will basically stay together. So that's why we do keep water here together. And our sodium chloride is a strong electrolyte, which means it will break apart into a sodium ion and a chloride ion here. Looking at our total ionic equation, we can find our spectator ions, which are the chloride ions on both sides and the sodium ions on both sides. And once again, that leaves us really what is taking place whenever we put together any combination of a strong acid with a strong base. It is really the H plus from the acid that will go find the OH minus from the base. And those two guys will basically make water, which is our net ionic equation that's happening here. That is why this is sometimes referred to, right, as an acid-base neutralization reaction, as they basically neutralize each other and you make water. This is also one of the three reasons we talked about as to why a chemical reaction takes place. Remember that a chemical reaction takes place based on either a transfer of electrons happening, which is what happens in redox reactions, a precipitate made, or a solid that's made, which is what happens in double displacement reactions that make a precipitate, or water is being made, which is the third reason why a reaction takes place, which happens here in our acid-base reactions. Any questions on that there? Now, a very common way that we kind of perform acid-base reactions is obviously like what you did on Monday and we'll do today, which is titration. So we do the process of titrations a lot of times, which are acid-base titrations. And in an acid-base titration, or in a titration in general, you usually will add a solution of known concentration to a solution of unknown concentration. And the purpose really is to try to figure out what the concentration a lot of times of your unknown solution is. So for example, we do these using a burette, and just like what you kind of did in a lab, one thing that you could do with your burette is fill it with some base. By the way, you could also fill it with acid if you wanted to as well. And then your beaker or flask or whatever it may be would have the opposite, so something like an acid. And in this situation, we could add our base to our acid, and we would add maybe a couple other things to this, maybe some deionized water, but also we would add an indicator. And an indicator is used to help us determine really when to stop the titration. And the place that we typically want to stop the titration is what is referred to as the equivalence point. And in an acid-base titration, at the equivalence point, the moles of acid will equal the moles of the base. So at the equivalence point in an acid-base titration, when you reach it, you have added exactly enough, say, moles of base to use up all the moles of acid that was there, which is why they're called neutralizing each other. Basically, you use both of those guys up at the equivalence point. So an indicator is one that will change color to indicate that, hey, you're pretty close to your equivalence point. You should maybe stop your titration. The one that you use, and is a very commonly used, is our friend phenolphthalein. And phenolphthalein is an acid-base indicator, and pretty much all indicators work over a pH range. So for example, phenolphthalein works over a pH range of like 8.3 to 10-ish. And phenolphthalein is colorless in acidic solutions. It's also colorless in neutral solutions, but it does turn a shade of pink in basic solution, which I'm assuming you probably saw on Monday, and we'll see again. In terms of phenolphthalein, around 8.3 is kind of colorless. And as you gradually go past that pH, it becomes more basic, which is what it is doing as it goes from 8.3 to 10, becoming more basic. It makes a much darker sort of pink color, if you will. And we use this to indicate where we should stop. So not all indicators are the same. They work over different ranges, and depending on the type of titration that you're doing, you may use a different indicator than, say, phenolphthalein. It would not be a great indicator for a different type of titration, but it works for a lot of the ones that we do. Now, when we do the titration, we do want to stop at the equivalence point. Sometimes people refer to the stopping point as the end point in the titration. And the end point in the titration is pretty much what it sounds like. It's where you laid up your titration. And if you did a good titration, hopefully the end point and the equivalence point should be close to one another. You don't obviously want to stop way before your equivalence point or way after your equivalence point. That is the point of it. Now, a very common thing that happens, say, when people do titrations is they add like one drop and go, wow, it was like no color. Now it's like super dark pink. Then maybe your teacher yells at you and says, that's too dark, try it again. Yeah, well, that's terrible. You shouldn't do those things. So let's talk about really why that happens. And if you take Chem 1B, you'll learn more about why this sort of happens. But if we look at what happens in a titration, say like the one you did last time, the one that you'll do today, and if we did a graph of the pH versus the volume of sodium hydroxide, it will typically make what is sometimes referred to as a titration curve, which kind of looks like this, like an S type of shape. And we'll just say our equivalence point is, in this ballpark-ish here. So what happens is, as you're adding, say, sodium hydroxide to your acid, the pH is starting to go up, And as you approach the equivalence point, you will typically see sort of a jump in the pH to the equivalence point. And then typically you will see another jump in the pH past the equivalence point. Now, the problem with sort of a jump in the pH there as we approach the equivalence point, we are basically going vertical here, right? As we approach the equivalence point, which means, does the pH change a lot as you go towards the equivalence point? It does, right? Because it's going vertical. Does it take a lot of volume to change the pH at that point? It doesn't, because pretty much wherever you stop in my blue spot, pretty much if you come down to the volume, it's pretty much the same volume, right? So when you go and you're close to the equivalence point and you add just one more drop and it goes like from like no pink to like a really dark pink, frankly, what you're doing is the pH can change a lot, right? In terms of one drop. And what that does for your indicator is, instead of being over here, now with just that one drop, maybe you're back in this range of it, and now you'll have a really dark pink color. So let's talk about the truth here. If I actually was able to hit the equivalence point right on the nose, or if I missed it by one drop, or was a little shy of it maybe by one drop, is there a giant difference in the volume of the equivalence point at that point? There's not. So really, if you're doing a titration, you're really, really careful, and you're adding slowly and going slowly, and you miss the equivalence point by a drop or two, doesn't really matter in your type of calculation, because the overall volume pretty much going to be the same. The reason why instructors yell at you that you should have the lightest color of pink is because, let's say you titrated like I did when I went to school, which was I just opened the thing up, let it drain halfway down, shut it, and I'm like, oh, cool, pink, I'm done, I'm going home, right? So if you titrated like me, you could end up with a pink color that will look the same way over here, right? Because that's going to look the same pink as it did, say, over here. And now, did I miss my equivalence point by a lot? I did, right? So that's why they typically will tell you, you want the lightest color pink. And because of that, that will actually put you closest to the equivalence point that you should be. And why they yell at you sometimes, you might need to do it again because it's too dark a pink. But in reality, if you are careful and you're progressing, carefully through your titration, not just randomly opening it up, shutting it, and just adding a bunch of base at one time, even if you miss it by a drop or two, it's really not that important, the color. It's really more important, kind of like the instructions are, that the volume that you use of the sodium hydroxide for each titration is relatively close to each other, which is why in the experiment they tell you, hey, it needs to be within like 1% of each other every your 2 titrations or 3 or however many you did. So that's really more important. Sometimes people get really hooked up on the color, like, hey, it's like too dark or something like that. But again, if you're very careful and you're sort of progressing slowly, even if you missed it by a drop, in the end, it really won't make that tremendous of a difference in the calculation, as long as you were careful and were not careful and ended up way over here where you would have the same color of pink. Any questions on that there? By the way, as you're approaching equivalence point, I'm sure you're probably told, right? You could do something like you'll see the pink kind of stay longer and longer, right? As you kind of get closer to the equivalence point. You could do something like add a half a drop, which is kind of let a drop form, wash it down with some deionized water, and kind of dilute it down. And that sometimes helps with the color, not going so dark pink. You could add as much deionized water as you want. It really won't affect anything in terms of the titration. Any question on titrations and the age-old question of, I just added 1 drop and it went super pink. I don't understand. Okay. All right, so when we do titrations and we have problems that we have to do, they really are, as I mentioned, 3 problems. The good news is in a lot of cases, they're this basic stoichiometry problems. You usually don't get too much of a limiting reagent type of situation happening in titration problems. You could, but in a lot of cases, you probably won't in these type of titration problems. So why don't we try one here, or why don't you give one a go and see what you come up with? We're basically kind of doing like a titration here. We're neutralizing an acid and a base. So what volume of 0.15 molar nitric acid do you need to neutralize 45 milliliters of 0.55 molar potassium hydroxide? So take a few minutes there and see what you come up with. Okay, let's take a look. So really, this is going to be a stoichiometry type problem. So we really want to follow our same steps. So we want to start with a balanced equation. So this is obviously going to be an acid-base equation, which means you should know that you should get basically a salt and water. So we'll start with our nitric acid and our potassium hydroxide here. And once again, we know that we should make water. And again, the water going to come basically from those 2 parts. And really the salt part will come from the other 2 guys put together properly. So that's potassium with a +1, that's nitrate with a -1, which means you should end up with KNO3 in this case. Just like normal, we want to make sure that it is balanced, which it does look like it is balanced. I think in this case, got a couple of hydrogen, a nitrate, and we got potassium. So I think we're good in terms of the balancing aspect of it. The next thing that we want to do is think about what is given to us. So we're looking for the volume here of HNO3, but we do have the molarity. Here for the potassium hydroxide, we have the volume and we do have the molarity as well. So first things first, we can get the moles from that piece of information there. We obviously cannot get the moles of the nitric acid, so that this is not a limiting reagent problem. This is just a basic stoichiometry problem. We want to think about where we want to end up. So for the nitric acid, if we think about molarity, obviously I have the molarity already. I am looking for the volume, which means really the one thing I'm missing to get to that volume is the moles of the nitric acid. And that's really where the stoichiometry part is going to come into play. Because we could get the moles of the sodium hydroxide, we then could use stoichiometry to get the moles of the nitric acid that we need. And then obviously we could get to the volume that we would need. So in this case, also remember that when we convert to moles, which is what we want to do here, we need to also convert our volume into liters. So we're going to divide this by 1,000 milliliters is a liter, 0.045 liters. We will use that to convert into moles, which is really our second step in our stoichiometry problem. We're going to use our molarity. Remember to also get rid of the big M and use moles per liter so you can see both of the units. So that 0.55 big M means moles per liter is sort of how you would want to use it, rather than just the big M where you forget about the actual liters part. So in this case, we do want the moles up on top, liters on the bottom here, KOH. That is going to cancel out our liters in this case. And we will end up with 0.0450. Oh, there we go. Times 0.550. Going to give us 0.02475 moles of KOH. Remember that we are not interested really in the KOH in this case. We do need to get to moles of HNO3, which is where the stoichiometry part comes into play. And from the equation, we could see that for every 1 mole of nitric acid, you get 1 mole of potassium hydroxide. So we're going to use that as our third step in our stoichiometry procedure. 1 mole of KOH will give us 1 mole of the nitric acid. That is what's going to allow us to actually get to the nitric acid. Any questions on that there? Now that I have the moles of the nitric acid, that really is sort of the last piece that I need. I now have the moles of nitric acid. I still have the molarity. I could rearrange that and solve for the liters, which would be the moles divided by the molarity. Once again, here I'm going to use our molarity as more of a conversion factor so I could see the units like that. So using my nitric acid's molarity here, I'm actually going to divide by it, which means the moles need to go on the bottom, liters up on top. And that will give us liters of our nitric acid, which is about 0.165 liters of nitric acid, which if we multiply by 1,000 would get us about 165 milliliters of nitric acid is needed here to neutralize this. So if we were doing a titration where we were adding nitric acid to our potassium hydroxide, in this example, we would have to hit 165 milliliters to reach the equivalence point. Question on that. It is really just a stoichiometry problem, same 4 steps, balanced equation, convert to moles, mole to mole relationship, and convert those moles to some other unit. So really the same sort of 4 steps. Yes. I'm going to tell you not to do that. And the answer is yes and no. So the answer is yes, it will work, but it really should be used more for a titration type, not titration, it really should be used more for a dilution type problem. And the reason for that is it will only work in titration problems where it is a 1-to-1 relationship between the acid and the base. So if you have an equation or stoichiometry where it's not a 1-to-1 relationship, you won't get the right answer. So for us, anything that's a titration problem, stoichiometry, you need to show work like this, some equation, stoichiometry part, and you'll probably always get the right answer. Will the M1 V1 equals M2 V2 work? It will, but in that specific instance where to one relationship is where it works. Sometimes confusing online. Sometimes people will say that is sort of the titration equation and stuff like that. And it does work going specifically for a specific type of titration. So it's best to save that one for dilutions and do these type of problems more as a stoichiometry problem. Other questions? All right, so let's take a look at another one here. What volume of 0.5 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfuric acid I think this is on your notes, so let's go this one here. See what you come up with. Look, so kind of same situation. If this was a titration, we're going to do some solution stoichiometry. We're going to start with our equation, which in this case is sulfuric acid plus some sodium hydroxide. Once again, you should know that's an acid and base, so you also should know water should be coming out there. And again, from those two guys, which means we want to put together the other two guys correctly. And again, that's sodium with a +1 charge, that's sulfate with a -2 charge, which means we should end up with Na2SO4 in this case. Now that we have the correct formulas, we want to make sure it is balanced, and it is not in this case. So I believe we need a 2 there. And I think we might also need a 2 there, and that should balance it up. Any questions on that there? Now we want to look at sort of what was given to us. So once again, here we are looking for a volume actually of the sodium hydroxide. We are given the molarity of the sodium hydroxide. And for our sulfuric acid, we have our volume and we have our molarity. So once again here, we definitely could get to moles from that piece of information for the acid. We clearly can't get to moles for our sodium hydroxide. So again, not a limiting reagent problem, just a basic stoichiometry problem. So we'll continue on with our normal steps, which is to convert into moles. And the ultimate goal here, right, is we're going to use the molarity here for our sodium hydroxide. So we have the molarity. We're looking again for the volume. So once again, we're going to use the stoichiometry here to get to the moles of the sodium hydroxide so that we can calculate what we're looking for. We're going to take our volume there of 125 milliliters. We're going to divide it by 1,000 to convert it to liters. Gets us 0.125 liters of sulfuric acid. We will use the molarity of sulfuric acid, and getting rid of the big M means we have 0.5 moles per liter of sulfuric acid. Once again, here the liters will cancel each other out, and we'll end up with 0.125 times 0.5. 0.0625 moles of sulfuric acid. Once again, we're actually interested in getting over here to our sodium hydroxide. So this is where the stoichiometry comes into play. Looking at the balanced equation, we could see for every 1 mole of sulfuric acid, we get 2 moles of sodium hydroxide. So that is the proper mole-to-mole relationship that we want to use here. So we'll take our 0.0625 moles of sulfuric acid. We'll use our stoichiometry from the balanced equation. 1 mole of the sulfuric acid, 2 moles of the sodium hydroxide. That's going to get us, times that by 2, 0.125 moles of sodium hydroxide, as obviously our sulfuric acid cancels out. By doing the stoichiometry part here, we now have, once again, our missing piece that we need to get to the volume of the sodium hydroxide. So once again, for our volume of sodium hydroxide, which would be in liters in this case, it will be our moles divided by our molarity. So taking our moles from above, 0.125 moles of sodium hydroxide. Once again, using the molarity of the sodium hydroxide, getting rid of the big M means that we will have 0.5 moles per liter of sodium hydroxide. In this case, we do want to put the moles on the bottom so that they cancel. And again, we can use this in either way, really, moles per liter, or a liter is 0.5 moles. The moles will cancel, and we will end up with here 0.250 liters of sodium hydroxide, which if you multiply by 1,000 is 250 milliliters of sodium hydroxide. Okay. Question on those steps. So to answer the earlier question, if we just rolled with the M1 V1 equals M2 V2, you would end up with 125, yes, which is not the right answer here. So again, really important not to use that equation in these type of problems because you might end up in the wrong spot. And it is still the same four step: balance the equation, convert to moles, mole to mole relationship, and converts to some other unit. Any questions on that one there? All right, let's try one last one here. Finish this one up. Let's try this one I just made up. So if in a titration, it required 63.5 milliliters of 0.375 molar calcium hydroxide to reach the equivalence point in a titration of 95.5 milliliters of hydrobromic acid. What is the molarity of the hydrobromic acid? I'll do it as well since I just made it up. Hopefully we'll get the same answer here. Okay, so once again, which really isn't put these guys together properly. Do some balancing to looking for the molarity here, which is our moles per liter of the hydrobromic acid. We are given the volume 95.5 milliliters. So that does mean that we do have the liters part here, but we do not have the moles part. So we're going to get that moles part really from the other reagent. And that is because we do have the volume and we do have the molarity of this guy, which means we could get the moles of our calcium hydroxide using some stoichiometry, right? That will then allow us to get over to the moles of the HBr that we need. So just like we've been doing, we want to make sure that our volume here is always in liters when we using molarity by itself. So we'll divide by 1,000, or you move the decimal place 3 places, gets you 0.0635 liters. So this will be our next step, which is taking the only thing that we could get to moles with, which is the calcium hydroxide, and using our volume and the molarity of our calcium hydroxide, which is 0.375 moles per liter of calcium hydroxide. Liters cancel, gets us 0.0635 times 0.375, 0.0238. I'll go one more. 1 moles of calcium hydroxide. Once again, though, we need to go from our calcium hydroxide to our HBr so that we can calculate the molarity. And from the equation, we can see every 2 moles of HBr, we get 1 mole of calcium hydroxide. So we will use that as our stoichiometry here to get to hydrobromic acid. So 2 moles of the HBr up on top, the 1 mole of calcium hydroxide on the bottom so that they cancel. Going to now give us, looks like times 2. 0.047625 moles of hydrobromic acid. Any questions up to there? Really, the whole purpose of this was to be able to get to the moles of the hydrobromic acid, which we now have from the stoichiometry. We also need to convert our volume hydrobromic acid into liters. So we'll also take that 95.5 milliliters divided by 1,000. And 1 liter gets us 0.0955 liters. That is what we want to divide by, as molarity is moles per liter. So 955 liters. And if we do that there, looks like 0.499. And again, the units here stay. So moles per liter of HBr. Or if you want, you can write 0.499 big M HBr. Any questions on that calculation?